All right, I'm recording now. I'm just going to go ahead and create a new blank project. I'm going to call this Hydro. I'll just call it Hydro. And you can use really any digital elevation model for doing hydraulic modeling. So if I create a new map, you can actually run the tools without even putting them on the map. I don't know if you all realize that in ArcGIS Pro. You don't need them on the map, but sometimes it's good to visualize things. I'm going to add in the Laguna Beach data set that we've been dealing with. I'm just going to open up elevation for now. All right, so all of these tools are under geoprocessing. If you open up geoprocessing and you go to toolboxes, you go down to spatial analyst tools, there's a tool set. That's what they're called. Tool sets are kind of like boxes within boxes. There's a tool set called hydrology. It's like, oh, did it disappear? There it is, hydrology. So a lot of these we've talked about, all these tools and how they run, okay, and what they do. So we should know what watershed does. We should know what flow direction does. If watershed is one that we described, talked about, but look, if you double click on it, you'll notice that it requires the flow direction raster as one of the inputs. So you need a flow direction raster in order for it to run. You also need a pour point. That's why I showed you that flow diagram before. So the first thing that you might want to do is flow direction, but almost every data set needs to have the sinks filled. So there's this tool that identifies sinks, and then there's a tool that fills the sinks. Oftentimes, it doesn't really matter what the sinks are, but it always helps you to understand where the sinks are to get a better idea is if you're doing something that shouldn't really be done, like you're filling up an area that is obviously really a sink. So sometimes I just run fill. That just takes care of it, but I always should run sinks to see where those sinks are. Oh, but you still need the flow direction first. Fill actually doesn't require flow direction. You just input the surface, interestingly enough. But in the background, it really is. It's creating flow direction like iteratively. So anyway, that's why I forgot that. So let's go ahead and create the flow direction raster first from the raw data set. So put that in. And one of the things that you're going to want to do, at least for today, and I usually do, this is not the default, but I always check force all edges. Wait, pretty sure that's the way it is. Let me look at the lab again. I have another data set for you to work with in the lab. Okay, so you can unzip if you want to. It used to be a slightly different. Remember to select the option to force all edges to flow outward. That's what we want. Okay. What that's going to do is anything on the outside of the data set is just going to assume there's a lower cell away from it. So typically you want to make sure that your area doesn't necessarily, encompasses an entire watershed. Okay, so force all those. So here's the drop raster. That actually is the raster that will show what direction the water flows out. I'm going to put that, I think if I actually just start typing, it'll put it in the cell. So I'm going to call this, oh no, that's the flow direction. I'll call this one flow dir LB, Laguna Beach. And then I'll call this one, oh, didn't copy. I'm also going to output the drop. The drop actually says how much drop there is. It's kind of like similar to slope, but it's just looking at the degree, the amount of the greatest slope. I mean, of the greatest drop. Right. Now, there are a couple of other models that are now implemented in ArcGIS. It used to be that D8 was the only model, but ArcGIS Pro have added some other models, and I'll bet if we read the extended help here, I'm just looking at the kind of tooltip help, but it would tell us a little bit more about these, and we could probably even cite a research article that we could use to read more about it. Right now, we're just going to do the D8. Hit run. Yeah. I did. I put something in the drop raster. If you didn't, don't worry about it. The drop raster, let's talk about each of these rasters. Here's the flow direction raster. Now, it's not symbolized the way that other one was symbolized, but we could change this to the symbology. We could choose unique values. And those are all the different unique values. So there's 1, 2, 3, 4. Look, there's plenty of them. So what does that mean? Well, if we hit, I'm just going to identify one of these values. So the value in that cell has a value of 4. So which way does the water flow out of that cell? 1, 2, 4. Yep, to the south. Okay, how about right here? Well, that one's 64. So that one flows to the north, right? I think that's what it was. I'm trying to find one that, because obviously there are some where it flows in multiple directions, but there's going to be a lot less of those where it has equal drops in 2 directions. Okay. I haven't found one yet, but it does occur occasionally, and that's why we have these other values. So we do have a few cells that flow in the direction 1 and 2, which is weird, because like I told you before, it's rare that you get a diagonal that flows the same as a straight out. Let's see how many of those we have. We can look at the attribute table and see how often that occurs. It'll have an attribute table because it's why does it have an attribute table? I actually have explained that before, but yeah, why does it have an attribute table? This one right here, elevation, does not have an attribute table. It's not just because it's unique values. Oops. It's because it's a discrete data set and it only has integer values. And actually, it doesn't even generate the attribute table unless it has under a certain number. I forgot whether it's 100 or so, but so you can't open the attribute table for that elevation data set. All right, so what does this mean, this attribute table here? Well, one of the things that it shows us is that there's a whole lot of cells where it flows east, even more where it flows southeast, a ton of them where it flows southeast, but there are only 5 cells where the drop was the same going east versus south. And that makes sense because that's not going to happen that often, that you have the exact same, especially since the run is different in those 2 directions. So the math works out 5 times where they have the exact same one. Okay. So a lot of these diagonals are pretty rare. This one's even more rare. 5, which would be 4 and 1 together. So that would be 4 is south and 1 is east. Usually that would be pretty rare. I mean, that would be less rare, but anyway. Some of these there's only one. There's only one cell that has a value of 45. No, I'm looking at the wrong. Well, eventually it becomes the wrong one. So actually, there's only one that has a value of 208. How do we get 208? I don't know. But there is only one way to get 208. All right, now the drop raster is optional. You don't have to output a drop raster. That's this one. So everywhere I click here, I get a value here, 181.3. Wait. That's the stretch value. Oh, that's elevation. I'll get it to show me. Oh, drop raster. Okay, here we go. So 16.6 here, 25 there. This is the amount of drop that occurs at that location. If I want it to look better, I could symbolize it using standard deviation. Let's say. No, it still doesn't work. More colors. Oh, so the very, very edge, remember all those values are flowing out. And so let's change this. So they're all getting really high values for their drop. Can you adjust the histogram? That's not letting me do that. But. Anyway, there is some variability there, but the ones that are flowing out have very, very high values, so they're not showing up. But we can inspect them by just clicking on them. So each of those, what those values represent is the drop in the greatest direction, what it is, what the value for the drop in the greatest direction is. Okay. All right, now we can get back to to identifying the sinks. So to identify sinks, we need to input the flow direction raster, and we need to specify the output for the sinks. Now, the output for the sinks is just going to be coded. It's either a sink or it's not a sink. So you're just going to get a certain number of values. If we went and read the help, what we're seeing here is the elevation data set. You see the values on top? If I zoom in here, these are all individual sinks. And what do the numbers represent? Well, if we read the help, it assigns a specific number to every single sink. How could that be useful? What if I was trying to get rid of all of the sinks except for a certain sink? Right. Now, how could I implement that in the GIS system? Let's say that I want at this sink right here, which is number 1703. I want that sink in there, but I don't want any other sinks in my data set. Well, I have this elevation data set where the sinks exist, and I also could create a filled version of the same data set. So I have a filled version, and I have the original version. And I have my thing that identifies every single sink. So could I come up with a raster calculator expression or a workflow that would get me a new raster that had all of the elevation data sets from the filled raster, unless it was sink 1703 and then use the elevation from the original raster? I could do that, right? Okay. It'd just be like in ArcGIS here, it would be conditional. I could say something like con, then the sinks thing. So if the sinks raster equals 1703, use the original elevation data set value. If not, use the filled value. I'm sure there's actually another way to do it. Maybe you were thinking of another way in your head, but because oftentimes in mathematics there's more than one way to figure out how to do something. But that's one way that I would do that. All right, now all these sinks are pretty tiny. My guess is that they're either areas that would naturally pool up and water would continue to flow, or they're just errors, simple errors in the data because of the elevation changes. So after inspecting this and saying, okay, well, those aren't, there's no problem filling these sinks. They're all really tiny little things. They're probably actually created from the DEM tried to remove all the houses. So these look like they're little house artifacts for the most part. All right, so at this point we might want to actually fill the sinks. So we'd run the fill command. By the way, this is just an alphabetical order. So if you're wondering why are we going through this process, why didn't the ESRI put it in a better order? Well, alphabetical order was good. So I'm gonna put my inputs here as the original surface raster because it's actually going to recalculate flow direction. I'm going to call this filled sink elevation. So now I'm going to have a new data set without any sinks. You can, if you want to assume that there are that sinks of a certain size would never fill up and would therefore should remain sinks, you could set a Z limit. What that means is an elevation limit. You say any sink that's deeper than this thing is probably a real sink, so I want to leave it in. You can do that. So that's what happens if you set that Z limit. If you set it at 5, it won't fill any area up more than 5 units, whatever your units are, and it won't allow the water to pour over. It'll continue to maintain that that's a sink. So I'm going to run this guy, and I get filled sink. Now, I'm not going to do this, but if I were to run sinks on this data set after calculating flow direction on this data set, I wouldn't have any sinks identified. That's what it does. So it's important to note that this data set here, I'm going to this isn't actually renaming the data set, but it is going to make it easier for me to understand it. I'm going to rename the title here as flow direction LB with sinks so that I know that's not the right data set. So if I actually want to proceed with this data set, I need to recalculate flow direction based on the new values. So that's right here, flow direction. Oh, by the way, I've had a few questions in last week's, or the week before. The lab, it's last week's lab. Looking at, I said, quantify I forgot exactly what I said, but look at find the difference between the two slope data sets. Well, right now, we could actually look at the difference between the two elevation data sets. So I could look at minus here and take the filled data set and the original elevation data set. I'm just going to leave the name the same. And what is this telling me? What do those values represent? The depth of what? The depths of the sinks. That's right. So what's that feature right there probably? Yeah, it's probably a creek bed or a pond that exists, and there's probably some feature here, whether real or whether it's like a road that actually has a culvert. So that's another reason why you fill sinks, because if there's a culvert, you're filling the sink, you're just saying, well, water is really going to flow past there. So you're getting rid of it. Let's look and see if we can see what this area is. So those are the deepest sinks that were filled. This was the deepest sink that was filled. Okay. So it looks like it's just a dry creek bed. Yeah, sorry. Go ahead. So, I did it as geoprocessing. What's that? That's what it should do. It's just an alternative way to execute the same command. So that is one of the the messages that I'm trying to present, is that these raster function chains are brand new things. They didn't exist before. Geoprocessing at one time was brand new. You had to type everything as a command. And so the software will continue to evolve, and there'll be new ways to do things. So what's more important is to understand that if I'm trying to find the difference between two data sets, I need to subtract those two data sets to show me that information. And then I can find the tool that does that. And so that's a great observation. Thanks for bringing that up. All right, so if I turn it off and on, you can see that this little creek bed here, the imagery could be slightly misaligned, I'm not sure, but that creek bed gets filled up. I don't know if this is like a dam. It's hard to tell if that's a dam feature or something. I'm not swearing, I'm just saying. Anybody ever go to like we went to what's the dam at Lake Powell? Out west. Anyway, the Glen Canyon Dam, I think is what they call it. You can take the dam tour. At the end, you take the dam quiz to see if you gained any dam knowledge. And the National Park Service is the one that has all these signage up. So I'm just quoting. Don't put that the teacher had a salty mouth or anything. Okay. So, all right, that's a little bit of a tangent. So the minus filled there, that shows one of the larger sinks, but there are other sinks. Here's another sink. Looks like a lot of these sinks are related to existing water features, which is fine. It's kind of interesting. Okay, so we're going to go back here to the geoprocessing, and I got to go back to hydro modeling. All right. Now, we still haven't calculated flow direction. We did once, but now we should calculate flow direction on which surface here? Yeah, filled sink elevation. So I'm going to call this flow direction filled. I'm not going to output the drop raster. It's kind of interesting, but we're not going to use it for any modeling later. So run it. There's less values. That's interesting. And why? Oh, I was like, why isn't it big? It's because this world imagery is everywhere in the whole entire world, which makes sense. That's why it's called world imagery. I'll just leave it on. All right, so yeah, there are less values. What that means is that there are less cases where flow direction is the same in two different directions. What's that? Oh, there are none. 1, 2, 4, 8. Yeah, cool. Well, my guess is that it actually enforces it. Like if we read the help, it actually makes it so that when you run it on a filled raster, the part of the fill process is it removes any ambiguities. I told last week. I told my family about how I couldn't say Shasta. Yeah, and my wife was like, "You're putting an extra H in there. Why are you doing that?" I was like, "I don't know." Yeah, so she laughed at me. That was what I was doing, by the way. I didn't even realize it. Shasta. Okay. All right. So flow direction. We calculated flow direction, and now we can go here, and all the rest of these build off of flow direction. Now, watershed only needs flow direction. You don't actually need to calculate flow accumulation for calculating a watershed. Okay. This one requires flow direction. Flow length requires flow direction. Most of these require flow direction. All right, so let's say we want to model, we do want to model streams, so we're going to go flow accumulation. So flow accumulation takes the flow direction raster, and we're going to call this flow accumulation filled. And, the input weight raster, this is how you could model a, like, let's say we're actually, well, let's go to this slide, the last slide. Let's say that we're actually trying to model how much water is going to flow off of every cell. Okay? So very, very simply, we can say that the surplus water that runs off of every cell can be modeled as the precipitation in that cell, okay? The input precipitation, the infiltration, and the evaporation. Now, maybe in a rain event, evaporation is negligible compared to these other things. Okay? But it could have an effect on very slow-moving streams. Okay? But let's look at those other ones. For input precipitation, you think that it's possible to have a raster cell that represents how much precipitation happened? We got news reports, right, where they must have. They show the accumulation of rain that happened at over a certain event, right? You've seen things like that before and on the news. So that data obviously exists out there somewhere. The input precipitation. Yeah, I mean there are issues. You're saying, if it says in this area you got 2 inches, in this area you got 3 inches, there are issues in terms of data resolution and accuracy, right?
There's got to be a formula to allow you to show how many inches would fall in a given space over a given amount of time.
Right.
There's got to be some kind of meteorological, somebody's figured out that formula. Sure.
Well, when they say there was 2 inches of rain here, they mean that 2 inches of rain, if I put out a cup of water, I would have gotten 2 inches in that cup of water. So models are often a simplification of reality, but what I could do is say in this cell, which is 10 feet by 10 feet, let's say, there's 2 inches of water in that cell. And so the amount of water can be calculated as 10 feet by 10 feet times 2 inches. So I would probably do, whatever 10 times 12. 10 times 12 would be 120, right? 120 inches by 120 inches by 2 inches. So that's the volume of water The input precipitation is the volume of water that hit that cell. Okay? And then how much was infiltrated, how much was able to go in, and we will talk about temporal modeling later, but you could actually be doing this constantly if you had some input on the time. So from, you have to pick some temporal time step, simplification of reality again. So it's 15 minutes. So for this 15 minutes, we got 2 inches of water. How much infiltration did we also have? And then we could explain how much water left a particular cell. Okay. Yeah. The what? No, I'm getting to what the weight raster is. So by default, if you don't select anything for the weight raster, everything has the same weight, and it's just telling you how many cells there are above that particular raster. Okay? But if we wanted to model something like this, what we could do is for every single cell, we could model the amount of water that was flowing off of that particular cell. Again, if we want to do time period, we'd say for a particular time period. And then the flow accumulation will multiply, instead of just ones, it'll multiply every single raster cell by that volume measurement that we came up with. And so every single cell will be the amount of accumulated water for that time period. Okay? And so if you did do time steps every 15 minutes, every 10 minutes, every 5 minutes, you could actually see how much water was in every cell for that particular time period. You can model the flow of water through the system. Okay. So that's how that could get processed. So using the weight raster allows you to determine that value. The weight raster multiplies a particular cell by a weight, which could represent things like the water flow. There's also trying to think of some other reasons that you would do that, but yep. So I'm just going to leave that blank, and then I'm going to run it. By the way, if I leave this blank, there's really no reason for this to be float, because it's just ones. Everything's a one. However, if your weight raster represented volumes, you would probably want it to be floats, because the volumes, you'd want to have significant digits and such. So I'm going to leave that as integer and then hit run. So now I have flow accumulation. Yeah. Oh, as a raster function? Sure. See if it looks the same. My guess is it'll be the same, but let's check it out. So I got my raster functions, and I'm going to run. There is a hydro there. Here's flow accumulation right here. So I'm going to run flow accumulation on my flow direction raster. That's the flow direction filled. And I'm just going to leave my weight raster. I'm going to actually type 1 because I don't know. I haven't ever run the flow accumulation in raster functions yet. But 1 is the default value. So I want to make sure that I get a default value. And then I'm going to choose integer because that's what I chose on the other one. And here I get an extra option to choose the flow direction type. So they've implemented those newer formulas in the flow accumulation they did implement them there too. Okay. So, I didn't see that. Okay, so create new layer. All right. Now, this flow accumulation does take a little while to run. And so, again, one of the drawbacks for doing this as a flow accumulation raster is that it only saves a virtual data set. Those look exactly the same to me. And interestingly, they have the same maximum value. So I'm inclined to think that they actually are the same. But if we wanted to check that out, we could click. Because it's hard to identify an exact particular one, I'm going to identify this junction between this river and that river and click it. And it should tell me, where's my... How come I can't identify anything? I don't know why identify stopped working. It's kind of annoying. Maybe you have to turn the window back on. Yeah, well, it looks exactly the same to me. I do want that, I mean, we do need that on to do the lab. So maybe I'll just try restarting ArcMap if that doesn't work. All right, so both of those look the same to me, personally. Okay, so flow accumulation. Now, let's look at watershed. Go back to geoprocessing here. We've got our watershed here. Oh, before I get there, we could, there's several tools. There's several tools that are useful for basically deriving stream networks out of them. So let's demonstrate this stream to feature. So first we actually have to decide what a stream is. Okay. The way I like to do this is to kind of, especially if I have imagery like this, is to kind of look and see, hey, is there a stream there? Well, it's kind of it's probably an intermittent stream, especially here in California. That looks like a stream. So I find one of the lower values in that area. Is there still a stream there? Yeah, it still looks like there's a stream there. There's a stream all the way back up into here somewhere. But now I don't even see the end of that line. I could change the symbology. In fact, sometimes it's good to just use classify. If you switch to classify and just change this to 2 classes, and then set your limit. So red, as we decrease this red value, we'll have more value. So if I go all the way to like, if I delete this first number, let's see how far it goes. Oh, that's going the wrong direction. Sorry. There's got to be a better way to classify these things in ArcMap. Anyway, let's see if this. If I delete this first number, what does it do? Yep. Okay. So see how it's created a lot more streams. Probably some erroneous streams right here. Look at that. Oh yeah, you're right. So they probably actually aren't. I mean, they're probably not really streams, but they are hydro features. because there are ditches on either side of the road. Good. So that number is probably a little bit too big, too small. So maybe we'll add a 1 back here. So as I make this number smaller, then I'll get less red and more yellow. As I make it bigger, I'll get, no, sorry, the other way around. So I want to make this, that's getting bigger. So anyway, you just play with that number a little bit, and you try to see if there really are streams at that particular location. You might even want to make this clear. Okay. So now, yeah, actually this is probably a better way to look at it. So see, when I make this number, I'm going to make it smaller first. You see how my streams reach out further, because I'm saying that it takes less flow accumulation to make a stream. Or if I make this bigger, make this a 9, then it takes more to become a stream, and so we get less stream areas. So I kind of like that. I think this still looks like a stream. That's kind of getting pretty close. And it's probably not actually a stream. But if you think about it, lots of times in California, you will get areas like this becoming flooded, particularly quick. This is right next to the edge of the canyon. Yeah. Now this is strange because water's flowing down through this street, and then it cuts over. Now this is really, really flat area. Remember the area by the high school is really flat. So sometimes hydromodeling doesn't do as well. What's that? But yeah, it probably would in that area. Okay. All right. Okay, when I say really flat, I should say it's pretty flat. Looking to be just not very flat area. Okay, so in order to create a stream raster, I need to actually code things as either being streams or not streams. So what I've done is establish a cutoff. I haven't really created a raster that's ones and zeros. So how could I do that to create a raster called ones and zeros? Well, there are a few different ways that we talked about earlier in the class, right? Reclassify. What's another one if I just want to do ones and zeros? There's the one I said earlier, the con statement. But even that is a little bit more than we need. We could just use, remember there's a tool called greater than, right? So we could just run greater than, or we want less. Yeah, we want greater than. So anything that's greater than that number, let's just round it off. 10, 0, 0, 0, or sorry. Yeah. If 10, 0, that actually needs to go in the other one. This needs to be the flow accumulation 1. So we'll call this one streams. So what we're doing here with greater than is saying if flow accumulation is greater than 10,000, assume that it's a stream. The output's going to be stream. So it's going to be 1. Everything else is going to be either 0 or no data. I'm not sure which one I'll do off the top of my head. I can't remember, but let's run it and find out. Okay, it looks like it's just zeros and ones. Before we run this this data set, this hydrology data set, before we run the stream to feature data set, let's let's actually read about what it does, what the inputs are. So it needs a stream raster. So an input raster that represents a linear stream network. I wish it would give us some more details about that. Yeah. So let's run it with this stream network and see what happens. Our flow direction raster, that's this one, flow direction filled. Run that. I didn't bother renaming it. Sorry. It has been a long, I was going to go to watershed next, but I thought it'd be good to demonstrate this. This is actually not requested for you to do in the lab. Big splash, that's probably what I'm going to get. Probably need to go read the help a little bit more.
I think it said that it has to be on a background of no data.
Yeah,
And we've got zeros.
that makes sense. So, so how could I do that? Oh, yeah, it will be beautiful. Yeah,
It's basically showing the flow.
the flow direction. It's showing the whole entire stream network. So for every single cell where it's flowing out. I did check the simplify lines, so it kind of makes it a little more simple. But yeah, this is the implied network that flow direction is creating. So that's kind of cool. I mean, it is kind of neat. So how would I've already brought it up now, so maybe I shouldn't ask the question, but how would I change the zero values to no data? Set null, I could use it. So streams, streams equals 0. If it's false, streams equals 0. Oh, change the. So if it's false, we want to leave it streams, or not. Yeah. So what this will do is says, okay, if the value in streams is equal to 0, make it no data. If it's not, then make it the value of streams, so those will stay as ones. That's how I did that. Run that. I'm going to turn off these guys for a second. So now I just have this that just has ones and no datas. If I go back to geoprocessing, hopefully that'll work. To do stream to feature, input the new streams, the flow direction data set. Run it again. Yep, that worked, and it took a lot less time to run too. All right, so those are the stream features that it pulled out using the digital elevation data set. Now, the reason that it looks like there's only data right here is because that's the case. Right? There's only data in that area. But now I have a vector data set that I could use, as I could either use it as like the truth. I could say here's all the rivers, or it would actually be probably more useful as a basis for starting to delineate river networks. It's kind of interesting here that water separates and goes around this neighborhood. Okay. Let's do watershed. That's the last one I wanted to talk about because watershed involves a few things, including this tool called Snap Pour Point. Really, you want to run Snap Pour Point first. You don't necessarily have to. Like if you turned on the flow accumulation data set, that we still have on here somewhere, where did I put it? This flow accumulation filled. And yeah, that's the one. I just symbolize, I'll re-symbolize that. I don't need to. Okay. So if I zoom down in here and made that my pour point, it would work. But sometimes that's hard to do, hard to get it exactly on that cell. And so it's easiest to run the Snap Pour Point tool. I recommend running it almost always because it makes it work better. All right, so the other thing that's nice about it is that it allows you to specify either a raster or a feature pour point. And what it does, the output will always be a raster pour point data set. So let's say we have a point, and that's our pour point, then we can specify that as a feature, like a point, not a raster. The raster it does require the raster to be like the one that we just created, where it's either coded as a number or as no data. No data means it's not a pour point. So we can't do ones and zeros, just like the other thing that we already did. Okay. Pour point field, what's that useful for? Well, you can't actually delineate more than one watershed at the same time. So if you run this data set, you'll get multiple pour points, and then you could run that into watershed, and you get multiple watersheds. All right. Let's actually. And then the snap distance is the distance that we'll search. And what it does is find the highest flow accumulation data set in that snap distance. Okay. So, do I have a... I have the start area. Okay, see how it's right there, my start area? That's not what I meant. Oh yeah, that's a polygon, right? Okay. Oh, but that's two things. Okay, so I've got two of these things. It's under class. There's two of them. Okay, if I zoom way out, not way out, but if I zoom pretty far out, it might be reasonable that somebody clicked there instead of clicking in the exact right spot. So what I could do is input my start area here, and my pour point field can be class, and then my flow accumulation raster would be that one that I created earlier. And if I choose to snap to my pour point, and I choose as my snap distance, let's start with 200. So it's within 200 meters, it's gonna snap to it. So I'm gonna run that. So here's my snap pour point. Zoom in here. Put it. There it is right there. I don't know why it didn't turn on. So it picked that point right there. See how it picked that point right there? I'm going to run this again and only choose 100. Now it picked, well, one of the 2 points picked was right there. So it's moving up My guess is I'm not going to be able to go much below 100. Sorry. I'll go to 50 now. Run this. So now the closest point the highest flow accumulation within 50 units, which I think are meters here, is up here. So here's the original area. And this is the pour point that it chose. Okay, because in this 50-meter circle that runs like this, it doesn't quite hit any of these guys. So that's the highest value right there. So that's why your snap distance matters. You want to choose a value that will get you onto the main stream. So 100 works. So now I got 100. That works fine. So that's within 100. That's the biggest stream. Let's see if we did 75. I think it's going to hit this area somewhere with 75. Yep, it hit right there. Probably even 60 will work. All right, so now it's picked. There are actually 2 start areas, so that's why it's picked 2 there. Okay, so now we could run, it doesn't really matter, as long as it's on the main stream channel. Now we could run watershed. So watershed takes the flow direction raster, and it takes the pour point data, so put in your snap pour point, choose the field, which is value, and then run it. And you're going to get a separate watershed for each value, so we're going to get 2 watersheds here. Well, we didn't get 2 because they're almost identical. No, they do change a little bit. All right. Now, in reality, that watershed, is that the shape of the watershed or is it actually bigger? Oops. It's bigger. We can tell that it's bigger because it gets to the edge of the map. Okay, so really, our watershed is bigger than what you see here. All right, so that's the process of stepping through each of these. You can do these all as function chains. I didn't do them as function chains. The problem is that there's no pour point raster. Sorry, there's no snap pour point. See that? So you have to get really, really precise and make sure you're defining the correct pixel. What's that? I did provide a pour point in the lab. Yep. And that pour point should be close, but my pour point, is it raster or a vector? Yeah, so it's still a vector, so you'd still have to convert it to run it as a raster function. But did you do it in geoprocessing or? Okay. Yeah, so it would work in geoprocessing just fine. I tested it in geoprocessing. I was going to say that. It looks like you can do this in raster functions, but you would need to manually create, in order to run watershed, you need to manually create that raster because there's no raster function chain for dealing with vector data. Yeah. The very first thing you did, like we did that last week. The very first thing you did was convert it to raster, and then you'd be all set. Yeah, so you just run this guy after you converted your vector to raster, and your data set would work fine. Okay. All right, so yeah, I demonstrated using the Laguna Beach data, but you're going to demonstrate, or you're going to do this with the data provided in the lab, which is other data. Okay. All right, so the first thing you're going to do, though, is to calculate these things by hand. So you're going to start out with your grid cell. Then you're going to determine the flow direction. And I want you to determine the flow direction manually. I mean, you could actually go to the thing I'm going to show you in a second and do that first, and then just write the numbers in. Okay, but the point here is for you to do it manually. So determine the flow direction using the 8-direction 4-point method. Indicate the flow direction by using an arrow in each of the grids. So do this only for the ungraded cells. It's kind of like it has the effect of checking that box. So only these cells you can calculate flow direction for. Okay. So let's do one right here. So for this cell, you're going to calculate flow direction, 67. So you need to find the drop to each of these cells, all of these cells. So you actually don't need to find all of them. Anything that's higher, you can just eliminate. So in this case, that is the highest value, though. So what's that? So you're saying it's going that way? Okay. Well, yeah, because that's 45, and that's probably less than, even though this is a shorter distance, it's probably less. In fact, you could calculate it out, but I feel comfortable saying, yeah, that's the right direction. Okay? But there are a few where they're really, really close. So the distance is, what's the square root? 100 times the square root of 2. That distance, that hypotenuse distance is longer. Just keep that in mind. I think there are a couple that'll get wrong if you don't keep that in mind. All right, so then you do the flow direction grid. Just indicate the values with arrows. You can put the numbers in. Then you're going to determine the flow accumulation grid. So you're just going to add up a number of cells that flow into every cell. And finally, if we were to define channels of cells with flow accumulation values over 2, which cells will be chosen? Just color in the values over 2. I'm going to add the circle. All right. Then we have to answer this problem where it gets a little more complex. If the annual runoff is given by the function runoff is equal to 0.15 times P minus 336, determine the annual runoff given the annual rainfall grid below. So this is just for a whole year. It's not a slice of time. So for a whole year, these are the rainfall values. So how much runs off every cell? So how do we do that? Well, you just take this value and input it into that formula in Master Calculator, and you get the result on this side. So, for example, 970 times 0.15 minus 336, that value goes right there. All right. Okay, so if these are 100 meter cells, calculate the mean annual stream flow drainage out of the outlet cell. So how much water is coming out of this cell? By the way, that's, if you get a different cell, then you're wrong. So that's where flow direction is going to go. That's where flow direction is going to go. And so you're trying to figure out what that is. Well, how would I calculate that? This involves thinking back to different types of operations. Okay? So basically, I'm getting a value here where every value represents how much runoff there is in millimeters per year. So getting millimeters per year each of those, and that's this dimension this way. We need to determine the meters cubed per year. So for each cell, how would I turn millimeters per year into millimeters cubed per year? Well, let's do it to meters. Yeah. Well, these cells are how big? I did tell you. 100 meters, okay. So they're 100 meters by 100 meters, and then the amount of water that's flowing off is some number, right? X. That's actually what we're going to call R. And it's measured in millimeters. So we could take that number and change it so that it was in meters. How do we change millimeters to meters? What's that? It would be divided by 1,000. You were on the right track. So it would be a really small number. So we multiply that number times 100 times 100, and we get the number of meters that are flowing off. So it's a really small number that's multiplied by 100 times 100, which is 10,000. 100, 100, yeah, 10,000. Right? That's 4, 1, 2, 3, 4, yeah, 10,000. So 10,000 times whatever you get here will tell you how much water is flowing off of every single cell. See what I'm saying? Right? So for every single cell, we know how much water is flowing off of it. So if I want to ask, what's the total amount of water that's going to reach this cell and flow through it, how would I do that? How would I do it manually, just first of all? Like if I knew which cells flowed into this cell, how would I come up with the total? Add them up, exactly. So if only these 4 cells flow into that cell, I would add the value of this cell, this cell, this cell, this cell, and this cell, right? Okay, now what if I had thousands of cells that represented a watershed? How could I tell the GIS to do the same thing as a single operation rather than calculating them manually? What's that? Flow accumulation. Yes, I could do a weighted flow accumulation, right? So I could run flow accumulation and do the weight. Now, there is another way to do it that's probably just as simple, still just one operation. Flow accumulation would requires me to, there's a way to do it with just the information that I've presented. In other words, I just have the watershed delineated, and I have the numbers that represent how much is flowing off. Even if I don't have the flow direction grid anymore. Yeah, sum them all. What type of sum is that? What's a watershed? It's just an area, right? Another way to think about that is it's a zone. So you could do a zonal operation where the watershed is the zone, and your runoff values per pixel per grid cell are the value raster. So either one of those will work. They're both good things, and they'll give you the answer that you need. So the weighted flow accumulation, one way, or just a zonal operation will also work. The weighted flow accumulation has the advantage that it doesn't require you to have delineated the watershed, but I'm requiring that you've already done that too. And then the zonal operation doesn't require you to input the flow direction. So it only requires the watershed. They both require the value raster. So this is either the weight raster in the flow accumulation calculation, or it's the value raster in a zonal operation. All right, so that's how you do that, and then you'll get a number. If you get a number, if you do the zonal operation, it will be the zone for this watershed. If you do the zonal statistics by table, it'd be the sum that you pull out for that zone. If you did the flow accumulation method, which probably might make more sense a little more intuitively. You just click on that cell, and it'll give you that value. Okay. All right. So then, what I want you to do, and really you could do this backwards if you really want to, is I want you to verify this. So these numbers are the same as these numbers here. So those are the same numbers, at least unless I messed up. Okay. All right. So what I have you do, this walks through it. I'll just demonstrate this real quick so it'll also be on video. I want you to copy this information and paste it into Notepad. Notepad works best for this, like that. Okay. Paste it in Notepad and then hit File, Save As, and put it somewhere on disk. I'm just going to put it in C temp. And I'm going to call this, it tells you that, hopefully I put that in there. No. Actually, it might, I'm going to test this. So you might have to have the .asc extension, but I'm just going to try it without it. So I'm going to call this elevation. So it's going to be called elevation.txt, and it's in ctemp. Then I'm going to minimize it. I'm not going to close it because I don't have hope that it's going to work. Okay, I'm going to insert a new map. I'm going to start with a fresh map here, and I'm going to find this tool that I told you to use. That's what this screenshot's about. It's in the same place under raster, ASCII to raster, or you can just type it, ASCII to raster. So you have to choose your ASCII file. It's in C temp. See if it's there. What did I call it? Elevation.txt. It's there. Okay. And then I'm going to call my output raster test elevation. And the output type integer is fine because those numbers are all integers. You run it. And what it does is it actually creates a raster using that data set. So if you right click on this and you say zoom to raster, it's going to go to the, it's going to go to 0, 0. So like, somewhere off the coast of Africa. But it doesn't really matter where it is. But we're just going to use the GIS tools to calculate the things that we already calculated. Right? So we need to calculate flow direction. By the way, why don't we, since we did this once using the other one, let's do this in, let's do this as a raster function. I didn't test this as a raster function, so hopefully it works. Okay, so I want to force all my edges, yes. And my input's going to be this test elevation data set. Run that. Okay. So I've created that, and this value here is something happened. There's only unique values at this point, so we're set. But something happened to my identify window. But you can see the value here is 2. Which way is 2? So that's that way. That's 2 as well, so that's that way. What's this one right here? It's that color 4, so south. Pointing, it's going that direction. Oh, 2 southeast. So that direction. And then this one is 1. Which direction is 1? That's east. And then from east, it goes east again. Then it gets into the dark, 16, west. So we got to sing. So, yeah, the purpose here is to compare.
Hey, Dr. Redford.
Yeah.
What tool did you use to get that?
I ran it in the raster function chain, I did flow direction. I wasn't actually planning to do raster functions. I just decided at the last minute. I was planning to do it in geoprocessing, but it would produce the same result to run flow direction here. So I'll just do this again. So under my test elevation data set, force all edges, output. I'm not going to output the drop raster. Run this again, and I should get the same values. Okay, they're different numbers, but yeah, those are the same values. Okay. So it'll work either way. The nice thing about raster chains, again, when you get done with it, you right-click on it, and you can see how you got there. All right. I'm sorry, could you ask that question again? Yeah, I didn't save it in Excel, I did it in Notepad. So if you I'll do this one, I'll demonstrate this one again. Copy, and then I'm going to open up Notepad. Not Notepad++. Just regular old Notepad. What's that? What'd you use? Oh, it'll work. It'll work there too, but, and then you hit, so then you paste it in there, and you hit save as, and I got my elevation.txt, so this is going to be rainfall.txt. And now, if I want to import that into ArcGIS, I use that ASCII to raster. ASCII to raster. I choose my ASCII file. It used to be that it had to be .asc, but I think ESRI realized they just made that up. So now it looks like it takes a .txt file. It's still it just needs to be in a text. It needs to be a text file. Okay, so I'm going to call this rainfall and run it. This one can also be, yeah, those are integers. That's fine. Right? So this is the rainfall for that area. Okay. So what you're going to do is follow this same process, but you're going to we just did this, the flow direction grid. Next, you're going to have to create the result of the filled grid. That's what's going to be here. Okay? So we could just go back here and run fill. And if you just like clicked the values, you'd get the values. Hey, is there a way in ArcGIS Pro now? I thought I saw a demo. If anybody finds it, then that'll be a bonus. But I thought I saw a way that you could actually have it label in the middle of every grid the values, but I don't know that off the top of my head. Okay. So yeah, you could just run all these and then click these buttons and fill it in. Okay. All right. So the only kind of thing that you got to think about here is when you're doing this part. So how do we implement this? So see this raster right here? That raster is this raster, same raster. Okay. How do we create this raster? Well, that raster is just this raster shoved into this formula. So you could do multiplication and then a minus, or you could just do raster calculator and you get this. Okay. All right. So what you need to turn in for this part is a picture of the process that you went through to get that. You can either do it as a raster function chain, or you can do it as a model, or you could just like actually draw it on paper. You know, I did flow direction first, then I filled the sinks. Okay, but it'd be better if you did it as a function chain or as a model. Then you need to email me a map. of the output of part 2. So that is going to be the result, whether you do a zonal operation or or the flow accumulation data set. Okay. Calculate the runoff at the given pour point in meters cubed, and include that with your answers. So you need to tell me what B is right here in what you turn in. Okay. All right. Now the next part is to do the same thing, but do it with some real data, and you're going to calculate runoff in a little bit different way. Okay. So what's going to happen is that there's a few different data sets, which I'll go ahead and just bring up here. I'll put these in the third window. A third map. Oops. I'm gonna add that data. I put it in C temp hydrolab. I gotta hit refresh, otherwise it won't show up. Okay, I'm just gonna add everything. It's in there. All right, what's that? Yeah, and you can figure out what the flow direction is at your house. It's all into your house. That's not good. Let's see. My house is not on here. Okay. So here is the digital elevation model. This is a rather coarse digital elevation model, and you can see it's an older data set that relied on automated photogrammetry principles, and there's some artifacts in the data. You can see the linear features, like Mississippi doesn't actually have these lines running through the data. Okay. So that might affect your answer, but that's okay. All right, then this data set is a percent impervious data set. I should put the source, but so the brighter areas have more runoff potential than the darker areas, which are open areas that are not impervious. They're not hard surfaces. And obviously this had some moment in time in which it was captured, and there may be areas now that are built up that weren't built up then. But I also don't have the citation for that data. Okay, this data set is an actual precipitation data set for a day. I don't know what day it was, but I got this off. I did get this off of the NOAA website. Okay, so it looks like it's fairly coarse data. It looks like it's been interpolated from points. I can tell that, and we'll talk about doing that in this class. But these were probably stations where data was collected, and then it was interpolated from those points to create a surface. I don't know why there's these other artifacts in the data. Not sure. But it was a much larger data set. It was a data set for, I think, all of the Southeast. So I cut it out to just be here in the same Hattiesburg area. So it wasn't originally meant to be looked at this detailed level of a scale, but we're going to do it anyway. All right, so what you need to do is you need to use the pour point data and the DEM to first derive flow direction and then derive a watershed. And you're probably going to need flow accumulation too. The cell size is 30 meters. Precipitation units are in inches this time. So we're going to do a little bit more unit conversion. So we're going to calculate the runoff formula different. Instead of the formula given in 1E, the runoff for each cell will be equal to the percent impervious layer divided by 100 times the precipitation layer. It's a simplification of reality. It's actually a little bit easier than this formula. This formula kind of assumed everything had the same runoff. Okay, it was a smaller area. So here we're saying, okay, it's the percent impervious, which we're just turning back into a fraction. So right now, percent impervious is in percent. So 90% means that 9 out of 10 droplets roll off, whereas 0.9 is a multiplier that we can use to modify the precipitation layer to figure out how much rolled off. All right, so how would we implement this? Once we have a watershed, we want to find out at the pour point how much water is going to be flowing past that pour point. How do we do it? Well, we can do it the same way as we did before, either through flow accumulation or through a zonal data set. But we're calculating this data set a little bit differently. We're not using that formula. We're just, let's calculate rainfall right now, just for fun. How do we do that? I'm sorry, not rainfall. This is precipitation's already rainfall. I want to count runoff. Using this formula, how would I do that? Divide by the impervious layer. So I've got my impervious layer right here. So Forrest is saying the first step is to divide, divide that. So impervious divided by 100, and we're going to run it. What happened? Why do we have a bunch of zeros and a bunch of ones? This is the right way to do it. We just need to change something else, by the way. So I wasn't trying to say, oh, you did it wrong. Okay. What can we do to overcome this problem? We've got zeros and ones. What do you think happened? Should the values range from 0 to 1? If they range from 0 to 100 and we divided everything by 100, so they should range from 0 to 1. It's just they should be a bunch of values in between 0 and 1. What do we call that when we have not discrete values, continuous values, right? So the way that we actually would do this is under environments. We could set. Maybe we can't do it there. Can't do it there. Okay, so the way that we could do this is this this float tool, which will convert a data set that is currently not integer values into a floating point value. So this will be imperv float. So now the values range from 0 to 100, but as floating point numbers. Now when we do the divide, we'll get better numbers. We'll run divide again. Impervious. I'm going to change this from 100 to 100.0. Run it again. So now we get values. Now look at that data set. Still it ranges from 0 to 1. But it looks more correct. Okay, what's the next step? So we've done this so far. Multiply by precipitation. So we're going to take precipitation. Oh, we got to multiply though. I guess theoretically we could do it somehow with divide. Multiply. It's times. Times. All right, then we divide it, then we take the divided output and we times that by the precipitation. And that, so when we run this, I could have just called this runoff. So this is the runoff. And it's measured in, I say that it's measured in inches. The runoff for each cell is equal to the percent impervious. Where did I say that it's? You will modify, first units are different this time. The cell size is 30 meters. The precipitation units are in inches. So what we could have done is convert before we actually did but now they're in inches. So how do we change inches to meters? Yeah, so we could run times again, and it's in inches, and we wanted to get it to meters. So 1 inch is equal to this many meters. So we multiply it by that number, and now we have runoff meters. So there's our runoff in meters, but we really want that's runoff in meters. We really want runoff in meters cubed. So how do we have to do that? Yeah, and it's so what we need to do is take the runoff in meters, and we need to multiply it by, what's that? Well, it's the cell size. Yep, so it's 900. We need to multiply it by 900. Because 30 times 30 is 900. So now that's how many cubic meters are running off out of each cell over. Exactly. Yep. So if you think about that cell as a 30 by 30 meter area that's receiving a uniform amount of rain, then the actual volume is the height of the water, measured in, this time, inches, times the cell size, the one dimension and the other dimension, which happen to be the same at this point. But you need to make sure the units are all in the same units in order for the answer to happen. Now we could have done all of this as one single raster calculator operation. Spatial analyst tools. So if we go back to impervious, we could do something like this. Float, impervious. What's that? So the depth is the height dimension. The depth of the water. So it's 30 times 30 times the depth of the water. It's like if I said, here's, if I had a rectangular box that was 5 inches by 5 inches, and I filled it up with 1 inch of water, how much water would be in that box? What's that? 25 cubic. How did you get that? Cubic inches. Length times width times the height, which was 1 inch. So in the same way, these raster cells, we're saying are filled with that much water. 30 by 30 times the height of the water. That's what that impervious surface model generated. See what I'm saying? All right, so here I'm just going to do this all as one big formula. I could take the float impervious divided by 100.0 times precipitation, and then I need to convert. What was that number? Yeah, there it is. Times, I'm going to do that first. So I'm converting the precipitation to meters right off. So this represents the precipitation. This big number represents the precipitation, the runoff, the amount that's available for runoff. The other stuff we're assuming infiltrated. And then we multiply that by 900. So that's the big formula. And when I say big, it still only has, what, three or four different terms there. So this determines, getting back to your question, this part determines the length and the width of the cell size, and this determines the height of the water that's running off, the amount of water running off. So we're modeling the amount of water running off of that cell. We're saying that some of it is going to stay in that cell. So what happens here is, let's say that impervious is equal to 100. Well, in that case, we get a value of 1 here. So all of this water is available for runoff, and we multiply that by 900, which is the length and the width. So we're saying whatever that value is, let's say it was 5 for precipitation, all of it's running off. If the impervious value was 50, then we would get 0.5, and we'd take the precipitation height value and basically half it to get the amount that ran off. It failed? And it has the exact same range, so it would work. Okay. All right, I messed up here. Or I just realized that I messed up from here. So when I said to create a map image, I don't want the map image of this. Okay. I want the map image of this part 2, because that's going to be more exciting anyway. Okay. In other words, I want the either the watershed defined or the flow accumulation value for part 2. Okay. So there's, now we have the runoff. The other part that you still have to do yourself is to calculate the watershed for the pour point given, or find out what the flow accumulation is at that location. The weighted flow accumulation, weighted by what? The impervious raster. Okay. That should give you the same number. All right, I'm going to go ahead before this gets too long. Let's see how long. This has been 1 hour and 40 minutes. That's a long time. I'm going to stop.